So what I'm going to be talking about in my section is a little bit about mass transport and how mass transport affects electrochemical processes. And this becomes quite important, especially where you're interested in understanding the kinetics of electrochemical reactions, because mass transport, which is the transport of reactants and products to and from the electrode surface, can actually significantly modify the response you see in an electrochemical system. And if you don't understand mass transport, then of course you can misinterpreting what is happening. So this is an overview of what I'm going to talk about. First of all, we'll discuss a little bit about the definition of reversibility in terms of an electrochemical system. And then we'll have a bit of a survey to the different approaches that are used for achieving high mass transport in electrochemical systems. And examples that we're going to go through are things like fast voltammetry, approaches that involve forced convection, that is where we accelerate the flow of the electrolyte across the electrode surface. Examples of that are rotating disc electrode wall jet and channel flow. We'll then look at microelectrode approaches, which are ways in which we accelerate the transport of reactants to the electrode surface by changing the geometry of the system. And then a short bit at the end, we'll talk a little bit about some of the work that we're doing in order to try and understand really fast electrochemical processes, especially those that happen at the gas-liquid interface. Okay, so this slide is a pretty busy one, but really it's just all about trying to discuss the fact that when we have an electrochemical process, typically we might have an oxidant in the bulk, which actually has to get transported to the electrode surface. Here's our electrode surface here, and it will get transferred by a mass transport process. That's this process here. Mass transport is driven by different chemical potentials of the species, or in simple terms, differences in concentrations. So, of course, we're consuming O at the electrode surface, and now we've got a concentration difference between the bulk and the surface, and so we will actually have diffusion from the bulk to the surface to replace this. So we can regard this as a step involved in our overall reaction. And of course, when we have a reactant that undergoes a reaction, this oxidant goes to reductant, and the reductant then actually has to diffuse back into the bulk. And because these processes happen one after the other, we can actually deal with them by saying the overall rate is just the inverse of the overall rate is just equal to the inverse of the electrochemical rate, which is this process happening at the electrode surface, plus the mass transport rate, which is this process of transporting the species from the bulk to the surface and then transporting it away again. And this formalism, this simple formalism, makes the assumption that what's happening at the surface is not affected by the mass transport, or at least it's only affected by the fact that it's actually replacing O at the surface. Actually, for more complicated reactions, which involve absorbed or multiply absorbed intermediates in this reaction, this sort of simple equation tends to break down. But in the vast majority of the literature, 99.99%, this equation is assumed to hold. Now, we define three different sorts of reactions. We define a reversible reaction. A reversible reaction is one in which this mass transport process, this rate constant associated with mass transport, is very much faster than the electron transfer process, which happens at the electrode surface. And what that means is that the concentrations of O and R at the electrode surface always follow the Nernstian, or the expected Nernstian concentrations or activities for the process. That is that this process always replaces any O that gets consumed is always very quickly replaced by O from the bulk of the reactant, and vice versa. In contrast to that, we have an irreversible reaction. In the irreversible reaction, the electron transfer process happening here happens very much quicker than the mass transport process. So that what happens at our electrode surface is very much dominated by this electron transfer process and the and the electrochemistry happening at the interface. And we can also define something which is sort of midway between each of those, a so-called quasi-reversible reaction. And the quasi-reversible reaction, we're sort of midway between these two limits. So typically this ratio of the mass transport rate constant divided by the electron or electrochemical process is somewhere in the range of 10 to 1, between 10 and 0.1, I should say. So actually, just go back. So we talked about this distance over which this transport to the electrode surface happens, and our question then is sort of what is this sort of distance that this mass transport is happening? And in fact, when we consider an electrochemical process occurring at a electrolyte liquid interface, we can actually define a number of different distances. So this is our electrode here. This is our electrolyte here. In principle, in the bulk of the electrolyte, we can actually have some sort of advection. We can have some sort of movement of that electrolyte that might be turbulent. It might be laminar, I should say, especially close to the electrode surface. It's liable to be very laminar. And of course, we will also have a stagnant layer adjacent to the electrode surface. Now, this stagnant layer is divided into a number of, is further divided into a number of different layers. We have the so-called hydrodynamic layer, which is the region over which the electrolyte is stagnant, that is, it isn't moving. And typically that has, for most typical electrolytes, is of the order of 150 to 1,000 microns thick. We have the diffusion layer, which is the layer over which reactants diffuse to the surface, and that is related to this distance here, where we've actually got the bulk concentration and diffusion to the surface. And that diffusion layer is typically 5 to 100 microns thick, depending very much upon the conditions in the system. And then we have the so-called diffuse layers, or the Debye layer. So this is the distance over which the electric field at the interface between the electrode and the electrolyte decays away to a bulk value. And you see the difference between the diffusion layer and the diffuse layer is quite significant. It's about 3 orders of magnitude. So the diffusion layer is actually relatively large compared to the distance over which the electric field decays away at the electrolyte interface. So how does this mass transport process, how does transport of our components that are reacting affect the electrochemical process? So we can sort of think about a simple thought experiment. You know, if we have our electrode here and we have the bulk solution here, as we start some sort of reaction occurring at the electrode surface, we will consume our oxidant, and of course we will end up with a chemical potential gradient or a concentration gradient, which will mean that O will want to transport, we will transport O towards the surface. And as we increase the current flowing through the system, increasing the amount of reduction occurring, of course we will consume more of that O at the surface until we get to the point at which all of the O which is diffusing to reach the surface actually reacts. And at that point, the effective concentration of O reaches 0 or tends towards 0. And that's shown in this diagram along here, where we plot the distance away from the electrode, which is this here, with our concentration of O. Okay, so here's our bulk concentration of O. that corresponds to the sort of red colour here. And as we get closer and closer to the electrode, it actually decreases because we're actually consuming O at the electrode surface. And of course, this bottom case corresponds to the case where O tends towards 0 at the electrode surface, and all of the O that's diffusing to the surface reacts at the surface. Now, it should be obvious now that under this condition, this bottom condition, we can't actually pull any more current through that electrode. We can't do any more reduction because all of the O that's getting to the surface is actually being reduced. And we can mathematically define that and define what will happen under those conditions, and define an overpotential, which is a transport overpotential associated with going from this situation to this situation. So this transport overpotential is associated with the shift in the Nernstian reversible potential associated with the change in concentration of O at the electrode-electrolyte interface. And in effect, what that means is that instead of having a current which increases exponentially, as we have here, i.e. that is a current which follows the Butler-Volmer type expression, as we see back here, Butler-Volmer expression like this. So instead of having a kinetic current which increases exponentially as we increase the overpotential, what happens is that the current initially increases, but then it eventually levels out until we achieve a limiting current. And this limiting current is the mass transport limited current. And that's what's shown here in the denominator, so that we see that this mass transport overpotential, that is a loss associated with the fact that we can't transport reactant to the surface fast enough, and that's dependent upon this limiting current. And just to give you an idea, 10 here is equivalent to about 0.258 volts at room temperature for a 1 electron process. So that you see that this curve will happen over a few hundred millivolts. Now, of course, in any real system, we will have some sort of mass transport limitation. And if we go back to this equation that we mentioned earlier on, where we said that the total current we can define the inverse of the total current as the inverse of each of these individual currents, this mass transport current, the rate of transport of species to and from the electrode surface, and the kinetic current, we can see that what we can do is we can actually invert this equation to determine the kinetic current if we know what the mass transport limiting current is. So J total is the current we measure, JMT is the mass transport limiting current, and so we can actually estimate what the kinetic current of the system should be based upon what we actually measure. And of course, that's useful because that allows us to actually transfer something like this mass transport limited current to a kinetic current, and that also becomes important as we see greater amounts of mass transport limitation. And this green curve here gives us the error or the difference between JK and J total as we actually go up this curve, so that we see that once we're down here at about 10% of the limiting current, our error or our difference between our kinetic current and our total current is already about 10%. Okay, so that's about 10% there, and 50 is about 10% of that. And of course, as we go up this curve, the difference between the actual current we measure and the kinetic current becomes quite large, and you can see that becomes several hundred%. So it becomes quite important to do these corrections for mass transport, because of course, if you don't, you are either underestimating, well, you're typically underestimating the kinetics of your reaction. This then comes to the issue of how do you, in order to do this equation, you need to know what the mass transport limiting current is. Typically in real systems, you actually might try and measure that. You might try and measure this sort of limiting current here. And that's an example, maybe far from the equilibrium potential. You can actually measure a mass transport limiting current. But actually the accuracy of your calculation of JK depends upon the accuracy with which you measure this mass transport limited, or this mass transport current. And this diagram here just gives you an idea of the error associated with any error in the mass transport limited current. So this is a 5%. If you overestimate your mass transport limited current by 5%, then at this potential here, you've got a 40% error in your kinetic current that you've actually calculated. If you underestimate your mass transport limited current, then for instance at this potential here, you also have a 40% error. So that you see, in order to actually accurately measure the kinetic current, you need to be able to also very accurately measure your mass transport current. And the other point I haven't mentioned is that this mass transport current, although it's treated as a single current density in the literature, actually this is also potential dependent. Typically, in the literature, people just use this as a single number without realizing that it is actually potential dependent, and it only tends towards a number when you're very far away from the equilibrium potential. So one of the issues we have when we do these sorts of corrections to find our kinetic current is being able to accurately measure the mass transport limiting current. And this is due not only to experimental difficulties of actually measuring this value. For instance, you might not have a very nice uniform current plateau, but also actually at the electrode surface, that mass transport limiting current might be different. So for instance, you might have different patches with different amounts of material on it. It might have different amounts of roughness, so that actually JMT might vary with position across the electrode surface. And of course, this equation assumes that JMT is the same everywhere. So one potential way around this problem, or at least to try and ameliorate some of the issues associated with this, is to try and increase our mass transport limiting current, because that then pushes this correction to larger and larger current densities. So now what we're going to do is talk a little bit about the different ways that we can actually try and increase this ratio of the mass transport limited current to the kinetic current. And really most kinetic, the rate constant for the electrochemical kinetics is typically, for fast reactions is of the order of 0.1 to 1 centimeters per second. So that really means that we want a KMT of at least 1 centimeter per second, and preferably of the order of 10 centimeters per second, so that we can always measure the rate of the electrochemical process. And so here are the different approaches that we can actually use. The first one, realizing that what we want to do is increase the ratio. One of the things we could try and do is actually decrease our current density for the kinetic reaction, that is decrease K0. The easiest way to do that is decrease the temperature. Another approach might be to decrease the number of active sites on the surface. So for some systems, as we'll talk in a moment, that becomes a possibility. But of course, the negative point of both of these is we have to question whether the mechanism remains the same. If we're changing the temperature, we might be changing the rate determining step, for instance, of our reaction. If we're changing the number of active sites, the question is, do those remain the same? The other approach is to increase the mass transport rate constant, that is, increase the rate at which reactants can get to the surface. And the approaches there are to decrease the measurement time, to increase convection, That is, increase the rate at which the electrolyte interacts with the surface. And the last example is to change the geometry of the system in such a way that we try and enhance reactant transport to the surface. And of course, the other thing that we can sometimes do is actually use secondary information in order to actually try and understand what the electrochemical kinetics are doing. So we're going to concentrate on this in the first step, looking at the temperature step, affecting the reaction through temperature. And I'll give an example. This is from a paper by Markovic and Ross, where they looked using a technique that we'll talk about in a little while, called the rotating disk electrode, to actually try and understand the hydrogen oxidation and hydrogen evolution reaction. Now, the comment from their paper is that the hydrogen evolution reaction and hydrogen oxidation reaction, that's what these two stand for, on platinum and acid electrolytes are among the fastest known electrochemical reactions, and it's experimentally very difficult to measure anything but diffusion polarization. What they're really saying there is the reactions happen so quickly that usually, K naught is so fast that usually all you measure is KMT. And so what they did here is they tried to slow down K naught by going to lower and lower temperatures, in this case down to 274 Kelvin. So this was using cooled electrolytes, and what you see is that as you decrease the temperature, you can actually see some effects associated with the hydrogen oxidation reaction. You don't see anything for the hydrogen evolution reaction, but you do see some slight difference for the hydrogen oxidation reaction. Different approaches to decrease the number of active sites. So, for instance, this is an example taken from this paper here, where they look at the oxidation and reduction of hydroquinone to parabenzoquinone, which is quite a fast process. If you study this, for instance, using impedance, which you'll see later on in this course, electrochemical approach, if you study it using impedance on a bare gold electrode, all you see is a so-called Warburg impedance. That is, you see this sort of 45-degree angle line, and again, you'll come across this later on, but really this is just telling you that all you're measuring is diffusion, the rate of diffusion of your reactant to the surface. So how can you actually study that process? Well, one way you can do that is by blocking the surface, and in this case what's used is a surface assembled monolayer. That is, you cover the surface with a monolayer of molecules that blocks the surface, which only has a few open sites on the surface that allow this reaction to occur. So in effect, what you do is you decrease the number of sites available for that reaction to occur, and all of a sudden you actually see something which you can actually see some sort of difference, and you move away from a reaction which is purely predicated by the rate at which you can transport reactant to the surface to one in which you can actually start measuring the electron transfer process. So that's an approach to try and decrease the electrochemistry. The other approach, of course, is to increase the rate at which we transport species to the surface. Of course, we have to worry that if we change the mass transport to the surface, we might also affect the reactant product distribution. So that's something we always have to take into account as well. The first example is to try and decrease the measurement time, and that is because if we have a planar electrode surface, what happens is that the current we measure is actually time dependent, and this is due to the well-known Cottrell equation for instance, for a potential step, and this comes about because, of course, at short time we have lots of reactant at the surface, and over time we deplete that reactant. So if we make if we do our electrochemistry at very, very short time, so that we don't have time to actually deplete all of our reactant from the surface, we can actually measure that reaction under the conditions in which we're not limited by mass transport to the surface. And this is an example here where when you look at, I can't remember what the actual species was that they were looking at here, but you know, you're looking at this reduction, and when you do it at a slow scan rate, it looks fairly reversible. You see the reduction and then the reoxidation. But as you increase the scan rate up to 10 volts per second, it becomes quite irreversible, and you only see the reduction step and you don't see the reoxidation. And this is just an example of going to faster and faster scan rates. You can actually start seeing the effect of only one of those processes and start understanding the kinetics. So the benefits of these fast voltammetric processes are that you can use for any sort of electrode material, and it's simple in terms of the equipment that you can use or you need to use. You just need to be able to actually do that voltammetry at very fast scan rates. The problems are, however, that of course you're only measuring your reaction over a very narrow period of time, so it's not possible to use this to understand what the steady state performance of a given reaction is. You can only measure what's happening at very short time. And the other issue is that if you have a rough surface, then that causes special problems with fast scan rates, because of course at low scan rates or under certain conditions at short time, you are only consuming the reactant very close to the surface, but at longer times it becomes much more complicated because you've actually got diffusion of different amounts of material to the surface. And for that reason, it can be somewhat difficult to model those results. And the other issue you have is that the capacitance of the electrode can become quite significant. The capacitance of the electrode that you measure the double layer capacitance is proportional to the scan rate that you use. So of course, if you scan 10 times faster, then your double layer capacitance, the current that you measured just due to the capacitance of the electrode, will be 10 times larger as well. So that can tend to overwhelm the signal that you're actually trying to measure. The other approach that you can use to try and increase your mass transport rate constant are so-called forced convection approaches. So in forced convection approaches, what you do is you stream the electrolyte over the electrode surface, and what you do is you increase the amount of mass transport to that surface through the fact that the electrode is being transported over the surface. And one of the benefits of this approach is that you can also use secondary electrodes downstream in order to measure the products that are being generated, and that's what I show here. Here's our primary electrode on which the first reaction is occurring. The electrolyte then takes our product downstream to another electrode where we can actually do further reaction. And that's that process is sort of called a generator-collector system. The most common method of forced convection is to use the so-called rotating disc electrode. Rotating disc electrode looks a little bit like this. Many of you might have seen it. It just involves a cylinder with an electrode in the middle. The cylinder is then rotated, and this acts as a pump. It sucks up electrolyte tangentially or sort of axially, and then flings it out tangentially. And the nice thing about this system is that it's very easy to describe that mathematically. We have the so-called Levitch equation, which tells us what our limiting current density is, and it's dependent upon the rate of rotation in radians per second. It's dependent upon the kinematic, or it's weakly dependent upon the kinematic viscosity. So the kinematic viscosity is just the viscosity of the electrolyte divided by its density, and it's dependent upon the diffusion coefficient of the species that we're actually reacting at the surface. And so we can see that from this equation, our mass transport rate constant is just equal to this. And if we plug in typical values for diffusion coefficients, rotating rates and viscosity of solutions, we see that the maximum KMT is of the order of 0.006 centimeters per second. So it's about 160-fold lower than we would ideally be if we really wanted to measure the electron kinetics of all the sorts of reactions that we're interested in. I should say that the maximum rotation rate that we have here is limited to about 10,000 RPM. Real systems typically don't go much above 5,000 RPM. This limit is due to the fact that above 10,000 RPM you start getting cavitation at the electrode surface. That is that the change in pressure is so great that you actually start getting bubbles formed just due to that fast rotation rate. So typically 5,000 RPM is the maximum. So the benefits of these rotating disc electrodes, they're quite good. You can actually make the entire system out of glass and PTFE, so they're quite easy to keep very, very clean and do very, very clean electrochemistry. I'm sure Yifan will talk about that in the next hour section. They're easy to configure and use. They're commercially available. We can perform these generator-collector type experiments, which for the rotating disc electrode is called the ring disc system, where we actually have the disc made of one material and we have a ring around the outside. And because any reactant that produces a product on the disc is then flung out tangentially past the ring, we can then use the ring to analyze what's produced. So for instance, in this example here, on the disc we have a reduction, and on the ring we've polarized at a specific potential so that the species that's reduced is then reoxidized, so that we can then measure the concentration of the species that's produced. And this can become quite important, quite useful. For instance, if you've got a reaction where after, for instance, doing a reduction, that species undergoes a reaction, some of it is converted to some other form, and then you use the ring to actually measure the amount of the reduced material that is still in solution. So you can actually use this to actually follow not only electrochemical kinetics, but also the kinetics occurring within solution of your electrogenerated species. What are the negative points? Well, as we mentioned beforehand, the mass transport rate constant is fairly low compared to where we'd want to be. And because of that, it means that we can typically only make our measurements over a limited potential range. And that means that often we can't actually make those measurements in the potential range where we'd want to be. What we have to do is actually make the measurements in a different potential range and extrapolate, for instance. The other issue is it can be very difficult to operate under relevant conditions that we might be interested in. For instance, high temperature is possible, but only up to about 60 Celsius, which is useful, for many experiments, but often you'd like to go to higher temperatures than that even. It's almost impossible to work at higher pressures. There have been some examples where people have operated at higher pressure as well, but that's quite difficult. Of course, if we're interested in gaseous species, and for instance, this is looking at the oxygen reduction process, then those gaseous species have to be dissolved in our electrolytes. So if we want to look at oxygen reduction, then we need to dissolve that oxygen in our electrolyte. And of course, the solubility of gases in solutions is relatively low, at least for most gases. Something like CO2 is moderate, but something like hydrogen or oxygen is actually very low. And of course, the other issue we have is if we're interested in a gas evolving reaction, then of course, because of the limited solubility of gases in solution, we will start forming bubbles. And as soon as you start forming bubbles, then this sort of Levitch equation starts breaking down, because those bubbles act to alter the mass transport adjacent to the electrode, and also act as barriers which limit the flow of current to the electrode. We can use many different sorts of catalysts and materials, but it can be difficult and time consuming in order to actually find ideal inks to deposit different sorts of materials. So this is sort of an example of different attempts to make different sorts of inks and deposit them on electrodes. Sometimes you get these sorts of coffee ring effects associated with Marangoni transport of the particles to the edge where the solution is drying. So it can be, that's sort of an art in itself of actually finding a way of depositing, materials onto these electrodes. The next approach is what's called the wall jet system, or the impinging jet system. Whether it's a wall jet or a wall tube system depends upon the relative diameters. So the idea here now is that for the rotating disc electrode, we rotated the electrode, and that acted as a pump, sucking electrolyte towards the electrode. In this case, what we do is we physically pressurize the electrolyte and actually squirt it through a nozzle at an electrode, so that the electrolyte comes squirting out here, hits our electrode, and then is actually deflected. And in the case of a wall jet, the diameter of the jet, that is this diameter here, is very much less than the diameter of the electrode. And for the wall tube, the diameter of the electrode is very much less than the diameter of the jet. So these give two limiting cases that can actually be easily mathematically analysed. And the mass transport rate is dependent upon the diffusion coefficient. Again, it's dependent upon the 3/4 power of the average velocity of the liquid down through the tube. And it's also dependent upon both the diameter of the tube and also the diameter of the electrode and the kinematic viscosity of the electrolyte. And with this system, we can achieve about a 4-fold improvement over what's seen for the rotating disc electrode. And here's an example of one of these sorts of systems. In fact, we actually ran one of these systems for quite a number of years in my laboratory. They're very nice in many ways. One of the really nice things you can do with these systems is you can easily switch the electrolyte that's flowing over the electrode. So here we have an electrode. We actually have the impinging jet here, and we can actually select which electrolyte actually bathes this electrode. So that allows you to do things like, for instance, deposit metals, in situ deposit metals on top of other metals, and actually make measurements. So that's sort of one of the really nice benefits of this sort of system, is that you can nicely change the electrolyte composition. It's very easy to keep these systems ultra clean as well. I'll just skip over this. It sort of just talks a little bit about the mass transport. Actually, I should say the mass transport is actually more complex and covers a different range of different regimes. That depends upon whether we're in this wall jet or wall tube regime. So therefore, the mathematics of the system is somewhat more complicated than for the rotating disc electrode. Actually, that's what I did want to mention, is that the generator-collector configuration in this system is also possible, but it's much more complex than, for instance, a rotating disc electrode. And typically these sorts of systems you have to build yourself, because there aren't many commercially available systems of this sort. Next approach is the channel flow system. So in the channel flow system, you have your electrode within a channel, and you actually flow your electrolyte down through that channel. Okay, and again, this is then you can achieve mass transport rates which are about 10 times faster than rotating disc electrode. So for instance, this is an example. Here we have our electrode. One of the benefits of this approach is you can do this generator-collector configuration. So your electrolyte that's flowing down here will entrain your product in it, and of course you can actually detect it at a secondary electrode. You'll see that the mass transport rate constant is dependent not only to the flow of the electrolyte to the third power, 2/3 power of the diffusion coefficient, but also the width and the height of the channel through which you're flowing the electrolyte through. Now, as I mentioned, the benefit of this is that we have 10-fold higher mass transport rate than the rotating disc electrode, and we have generator collector configuration. We also have the opportunity to be able to change the electrolyte composition during the experiment. So of course what we can do is if we've got the electrolyte flowing down through here, midway through we can actually change the sort of electrolyte that's flowing through here, so we can change the local conditions, and we can use that to actually prepare our electrode or absorb a species on our electrode and then go back to a different sort of electrolyte. So that's a really nice sort of system. You can operate at higher pressure and temperature. So here are systems in which have gone up to much higher pressure, so you can pressurize them. And the other thing is that they're actually suitable for integration with other techniques, and as I'll show you in the next slide, for instance, you can integrate them with X-ray or, for instance, IR and EPR measurements. Example shown here where a flow system through here has been, can be used to actually look at the surface with X-rays, so you can actually do those sorts of measurements under flowing electrolyte while probing the surface with X-rays. So that's sort of, one of the really nice positive things about these systems. It gives you a lot of opportunities. The real major issue about this is that you can't make a large amount of the system out of glass and PTFE. And these systems actually typically have very high surface area to volume ratios. That is, that the wetted surface of the electrochemical cell is very, very large compared to the volume of electrolyte. And that means these systems can be very difficult to actually keep scrupulously clean. So that really being able to do nice electrochemistry where you can actually keep your system super clean can actually be quite difficult. So there's sort of benefits and negative points of this. Now the last large-scale or significantly used approach I'm going to talk about is one which involves a geometric change. So in this system we don't actually flow the electrolyte. The electrolyte is static. But now what we do is we shrink the size of the electrode. And this is the case of what are called ultra-microelectrodes. So for an ultra-microelectrode, the mass transport limiting current is dependent upon the shape factor and also the radius of the electrode. And the typical radius for ultra-microelectrodes is less than about 30 microns. That is, we choose a radius which is less than the typical diffusion distance that I mentioned earlier on in this lecture. And that's the domain under which these ultra microelectrodes work. They work within the diffusion layer distance. And of course H depends upon the geometry, and here's a whole range of different geometries for different sorts of ultra microelectrode. Here's an example of a cone. Here's a planar system. Here's a hemisphere, and here's something which sort of approximates a sphere. So you have a whole range of different geometries that you can actually look at. The benefit of ultra microelectrodes is that in principle you can go up to very, very fast mass transport rates, maybe up to 20 centimeters per second for really small electrodes. Just to give you an idea, a 30 micron diameter ultra microelectrode has a mass transport coefficient, has a KMT, which is equivalent to about a rotating disc electrode, which is rotating about 1,000 RPM. So at 30 microns, you've got something which is, approaching as good as you can do on a rotating disc electrode. As you go smaller, as R decreases, you see the KMT increases. And the reason why these systems work so well, or the reason why mass transport is so fast, is that now instead of relying on planar diffusion, which occurs when electrodes are larger than about 30 microns in size, larger than the thickness of the diffusion layer, Once those electrodes are wider than the thickness of the diffusion layer, you rely on planar diffusion. Once you're smaller than the thickness of the diffusion layer, those electrodes have hemispherical diffusion towards them. And of course, if you have hemispherical diffusion, what happens is that the area over which your reactant is diffusing through in order to get to the electrode surface increases hemispherically with time. And so that means that the rate of mass transport does not decay away with time, even though the electrolyte is static. Okay, so for a normal planar electrode, you'd get this T to the minus half dependence, which even for a microelectrode, at very short times, you see you've got a small amount of planar diffusion. That is all of the reactants are actually traveling normal to the electrode surface. But then at longer times, you've actually got hemispherical diffusion. The reactant comes from a hemispherical front. That means that for these, that means for these sorts of electrodes, you also have a limited time over which you can actually make these measurements, because at some point this hemispherical growth will actually exceed the distance associated with your diffusion layer. Okay, and you'll actually start getting some sort of, instead of actually having a nice uniform diffusion to the surface, you'll actually start getting some sort of fluctuation. And so mass transport's up to 1,000 times faster than the rotating disk electrode. One of the other nice things you can do here is you don't have to use a liquid electrolyte. Catalysts in contact with solid polymer electrolytes. So one of the nice things here is you don't have to use a liquid electrolyte, and you still get fast mass transport. So what are the negative points? Well, because you've got very fast mass transport of reactants to the surface, that also means you've got very fast transport of any contaminants to the surface as well. So you have to be scrupulously careful about contamination control in these sorts of systems. The other issue is that because the electrodes are much smaller, it means your currents are much smaller as well. So for instance, in this example here, we were able to make these sorts of single supported metal particles on a carbon electrode down to about 30 nanometers in radius, about 60 nanometers in size. And down at this level, the currents we were measuring were around half a picoamp. Okay, so the ability to actually make the measurement becomes really critical about having a very noise-free environment. Depending upon what you're studying, if you're just studying a surface, it can be actually quite difficult to actually make those surfaces. And the other issue you have is statistical significance. If you're only making, because the electrode is actually so small, you have to worry about whether, if you just make one measurement, whether that is statistically significant. Ideally, you'd want to repeat your measurement many, many times in order to actually make sure you've got a statistical sampling of different sorts of particles. Okay, so this is then a summary of the different sorts of approaches with sort of the comments. We go all the way from the rotating disk electrode, which is probably the most common method that's used, which is very useful. It's commercially available. Ultra micro electrodes are probably the next most common method that's used, although it's sort of somewhat limited in sort of the sort of things that we can do. And in between, we have these two processes, wall jet and channel flow. And the benefit of both of these processes is it's very easy to change the electrolyte that's actually flowing over your electrode, which is much more difficult in both of these processes. Lastly, I want to talk about a different approach which we've developed over the last few years, which is based upon the idea of trying to study systems associated with gas reactions, which are very common in electrochemical type reactions, for instance, oxygen evolution or oxygen reduction, hydrogen evolution, hydrogen reduction, CO2 reduction, for instance, even nitrogen reduction. And this is sort of a new, or at least a redeveloped approach, which was the original idea comes all the way back from the 60s in this paper here. And what we've done is we've re-engineered it, made it much, much better so that we can actually achieve the same sort of performance that was achieved in 1967 with 100,000 times less catalyst. And the idea here is to instead of having transport of our reactant, which in this case is a gas, instead of having that transported through the electrolyte, we transport it through the gas phase for as long as possible. That is, we keep it in the gaseous phase up until we get right up to the catalyst where we want the reaction to happen. And using this approach, we can actually study things like the hydrogen reaction, which, if you remember earlier on, the quote from the Markovich paper, where they said, the hydrogen reaction is probably the most kinetically fast common electrochemical reaction, and something which most people only ever measure mass transport on. And we can use this approach to, for instance, study the hydrogen reaction. And we estimate that the mass transport coefficient of this approach is about 30 centimeters. And the way that we do this is we make something which is very similar to a fuel cell type electrode. We make something which is very, very similar to a fuel cell type electrode, in which we actually have a porous substrate. We have a porous substrate which has actually got pores in it, and we deposit our catalyst on the surface of this membrane, and we actually keep gas transport to and from the catalyst in the gaseous phase. And this means that the diffusion distance, which is our mass transport is dependent upon the diffusion distance, is kept much less than 100 nanometers, so that actually we get very, very fast mass transport. And if you compare this to, say, a typical fuel cell or electrolyzer electrode, what we do is we actually shrink the support by at least a factor of 20 to something which is only 10 microns thick, and we make our catalyst layer about 14 or 15 times thinner, so that it's only a few hundred nanometers thick. Is actually have we can support our catalyst in the pores of this material. So here's our catalyst supporting the pores. The gas can go into the pores as shown here, and our protons are reacted, or our electrolyte is wetting the catalyst from the other side. So we actually have ionic transfer on one side and gas phase transfer. And so this gives a comparison from what we see on a rotating disk electrode. This is hydrogen oxidation going into hydrogen evolution on a rotating disk electrode. And you see that on the rotating disk electrode for hydrogen oxidation, you just get a mass transport limitation. As you go down to hydrogen evolution, you start getting bubble formation down this side. Similar for oxygen reduction. Here's oxygen reduction. You actually get a limiting current associated with the fact that you just can't transport enough oxygen to the surface just because of mass transport, If you overlay the results we get on our electrodes over this, you see that the oxygen reduction goes shooting off down here. Our hydrogen oxidation goes up very, very fast and goes down very, very, very fast. And in fact, you actually have to zoom out by a factor of 200 in order to see the entire structure. So this is now what our hydrogen oxidation looks like, and this is what our oxygen reduction looks like. So this is sort of a very nice approach which allows us to study these sorts of gas phase reactions at really high mass transport rates, and to understand something about their true kinetics, something which has actually been very difficult to do in the past. And I'm just going to skip over this because we're running out of time, just to say that we can also use this approach for oxygen evolution. So here's where we look at oxygen evolution on these sorts of electrodes, and even using very, very low loadings of 50 micrograms of iridium oxide on the surface, we can actually see current densities up to several hundred milliamps per square centimetre at very, very high over potentials without the formation of any bubbles. So that's sort of a really nice thing about this approach.
Anthony,
the other nice thing about this approach is that we can actually couple it to other sorts of systems. So we can have so-called electrochemical processes where we couple our electrochemistry to things like mass spectrometry. So here's where we do methanol oxidation on our electrode, and at the same time, because we've got very fast gas transport, we actually can couple that to mass spectroscopy as well. So that's sort of an idea about sort of future high mass transport electrode structures and how we might be able to actually study electrokinetics in greater detail. So really short conclusion, because I've sort of run out of time. If you want to measure electrochemical rate constants, actually you need to make sure that your mass transport rates are at least 10 times faster. And that the mass transport rate is dependent upon the diffusion coefficient of your reactant, which typically you're not going to have much control over, divided by the diffusion distance that species is diffusing over. And this is something that we can actually control by different sorts of experimental configurations. And with that, I'm going to finish. I'll just see if there are any questions. So the first question, sorry. The first question is it possible to use activity instead of concentration in the Levitch equation to estimate the limiting current in a non-ideal system? So, of course, you're quite correct that we should actually use the activity rather than the concentration. Strictly speaking, although I've used concentration in my formalisms here, actually the activity should be used. It should in fact be the molality times the activity coefficient for the given system. So you should actually correct for non-idealities. So that's quite correct. So the next question is, in an experiment oxygen evolution reaction, for example, what would be a good way to know the kinetics we are measuring? So I suppose the question there is what you're trying to ask is, how do you know if your reaction is being affected by a mass transport limit? Okay. And I suppose the answer to that is that it can be very difficult to know if that really is the case. So one of the big issues with oxygen evolution, of course, is that for most configurations of oxygen evolution, you actually have bubbles formed on the electrode surface, and that actually limits mass transport. That limits, and that also affects the IR drop to the electrode surface. So of course, one way that you can actually see if you're under mass transport limitations or being affected by mass transport is to do electrochemical impedance. So typically with electrochemical impedance, you'll see what's called a Warburg type response if you're in a mass transport limiting condition. So that would be one way.